whenever you guys would like, can you talk through what you built?
Sure. So to give you the viewers a little sneak peek so that they don't click off. So we built a GUI to draw numbers.
Portrait of a team.
And there you go. Just kidding. It's a Python convolutional neural network. And it predicts the number that you draw on this GUI. Now, I'm sorry if it sounds like I'm talking a little silly. I am very tired. This was my home for the night. But now we'd love to inform you on how it works. We'll come back to the GUI.
Alright, I've prepared a nice little PowerPoint presentation. Stuff that I learned in 4th grade. I just slapped it onto it. Okay, now, so
Okay.
we have our input image, right? Which is, it's a number, but in this instance, it's a car. We have two convolutional layers. The first one is the largest, and then we have a max pooling layer immediately following it. I will explain what each of these layers mean, but it's this sequence followed by the same sequence of convolution and pooling, and then we flatten it at the end, and then generate our predictions of 0 through 9. So, what convolutional means, it's a very simple, I try to simplify as much as I can. So, we have 28 by 28 images, but let's just take a 4 by 4 image, for example. So what we're doing is, we have a kernel size of 2 by 2, and we are sliding the 2 by 2 kernel across the image, with a stride of 1 each time. And then our output is called a feature map. This is the output of the element-wise multiplication and summation of this filter with this section of the image. And we just repeat that for the whole image until we have like the entire 3 by 3 output feature map. So this is what the convolutional operation does. And this gives an idea of the spatial and the edges of the image. This is how we learn like the features of what makes up a car, what makes up a digit. We learn all the gradients. And then immediately after that, we have a max pooling layer. So we take that feature map that we just generated, but I just did 4 by 4 for the sake of simplicity. And then we infer another 2 by 2 kernel. And then, but here at this time, we take the maximum at each kernel, more or less. And then what that does is it shrinks the image down into something that's more digestible, so we don't have as much information to process. And the goal of these two layers is to almost mimic the human retina or the human visual cortex. It's saying that, let's use a dog for example. So Comp2D, all it does is after applying different filters to the image, you can see, these are certain outlines that make this image distinct. And then max pooling just shrinks that. So that's the entire goal of this network.
Okay.
So.
And sorry, he kind of gave you this was the presentation that we created in case it didn't work, so that we gave you the full rundown to kill some time. But so building anyone who's done anything in Verilog knows that little code doesn't go very far. A lot of code goes very not far, and so in order to facilitate writing a neural network in Verilog, we now arrive at our second final project, Verithon. So, while Kenneth was developing the...
You sound like an infomercial, man.
I sound sleep deprived. So, while Kenneth was training the models, I was building this library. And so, in general, it's basically Verilog in Python. And so, what I've done is I've overloaded all of the syntax of Verilog and made it in Python. So like you have class structures that are modules, And inside these modules, you have your variables and your ports, which you can easily define once you initialize the module, you have access to a library functions like add_var, which adds a new variable where you can also specify the width. Like, let me go to a better one, like layer. Let's go to a specific layer, knet v3. We'll go to the convolutional layer 2D. So you can create weights, biases, or just arrays, I guess is a better way of saying it. Where are we? Different registers, whatnot. Okay, yeah, you get it. You can declare variables. We're all on the same page. So each Verilog, each V module object has a function called generate. And this generate function, it returns a V block object. And this V block object is basically a list of what I call V expressions. And they're just strings, but they're overloaded Python objects where, for instance, if you did a statement like, these are two signals, m.ti plus m.ii, very well, clearly named. Let's see, what file is that? That was the 2D. So this was, and I'll come back to the states in a second. This was set imp address. So right here, so this is ti plus ii times this. So n is a constant. It's 28, but each signal object has a bit width associated with it. And so when you add those two signals together, it creates an output signal, MTI, II, whatever the concatenation of that is. But then when you multiply it by an integer, it automatically casts it to that of its bit width and outputs it to this code. And so it makes writing Verilog much easier and much clearer. But by far the most practical and useful part of this is the state machines. And so what I've implemented is the ability for your Python module to infer based on the structure of a Python object, like what it would be in Verilog. So if we go to the, just to give you a brief overview, actually, this might be easier. And so this is all over the last 2 or 3 weeks.
Also run one of your test matches.
Oh yeah.
Just straight up get model sim with all the waves.
So so this is the source code for it, and so in this core file, we define different object types. That all the syntax is in this V syntax. Let me see if I can. Okay. We're getting better monitors one day. So, like, all of the syntax is here in this V syntax file, and what you'll notice is that I've basically built this entire language from a list of strings. So the V block object, new lines of code are delimited by commas, like a list, right? And so, like, let me show you a implementation of this, the V if statement. Oh goodness. Just give me one. So, just like a normal if statement in any language, right? You would expect the if statement, the if word, a predicate, right? Something in parentheses, and then everything that follows after, right? And so the v-if is a function that takes in one argument, the predicate, and then returns another function, which takes in as many lines of code as you want. You delimited by comments, right? So it's intuitively what you would expect in a high-level programming language, and so so you have these low-level concepts, right, where it's a lot of the statements, the syntax is overloaded to make it easier to develop. But not only this, I mean, here's an example of. Let me show you an example of like and it doesn't just make it easier to do like individual statements. Here's one. So I created a list of wires right here, molt outs. Okay, so this is a list comprehension syntax in Python. It's basically saying I'm creating a list of self.w row number wires, w wires, right? And then each of them are named molt out 0 through 1, 2, 3, 4, right? So if we take a look at the output of this, here's our molt out 0, 1, 2, 3, 4. So number rows is 4 in this case, right? And so it defines them all with the right variable or with the right bit width and whatnot. And so, but notice it's not just assigned to like a single object. This is a list of objects. And so, let's say I want to do something with that, like maybe sum it. So here, I set the output data. Let me show you its implementation first. The output data of this module is equal to the sum of all those multiplications, and then this comp2d bias, right? And so I set it. Every signal has a set function. That's how you can set it equal. It infers whether or not it's a wire or a register. And then there's this vsum function, which is kind of like that if statement, a syntax that's overloaded, where you can give it as many lines of code as you want, and it sums them all together, returns that expression, right? And so an example of basically it allows you to rapidly create a massive number of signals to where operations that you would normally think need to be clocked can be unclocked, because you just, like, a clocked operation is just sequential steps, right? But like a lot of the times it's just so that you don't have to write out each of those sequential steps. Like if something takes like 80 steps, well, you could really do the same thing if you just wrote the same like wire followed by another wire. I mean, it's not spatially efficient, right? But if you're trying to be, if your space isn't your concern, if you're trying to be cycle efficient, right? And so an example of this is I made
vision.
Yeah. So Ken said that Ken told me how to. He wrote a Verilog module for division, right? And then I implemented it in mine in my code. So where is it? Test ops. So. Oh, yes, I love when it gives me errors. Okay, we're gonna do a little sneaky trick here. I know the guy who made this, so.
You're automating the feature, my friend. I think Chris Batten made something like this. Joe just upgraded it to Python 3.
There we go. Okay, so so this module just, in it I have a divider module that it made, an unclocked divider, right? And so take this. Ken made me take it out. He didn't like it.
It's too slow. That's what I do.
Sorry, you can skip forward 15 seconds. Right, that's because I took it out of signed. Div no clock. There we go. Okay. Now we're cooking. Okay, so don't look at the console yet because you're getting a sneak peek. I'm just gonna exit out all this junk. So where all this code outputs to is this Verilog folder right here. And look, I'll delete it. It's terrifying, right? Deleting code. No, that's not the right command. If you look, I run that file and then this gets generated again. Sorry. Here's this ops test bench. I'll get back to the test bench in a second. So here's the sign divider, right? It's fairly concise. It takes in an int width and a decimal width, so it's a fixed point divider, and so it's a function. It's parameterized based on the int width and the decimal width, and so it creates this fairly concise module. And then here's its unclocked counterpart is this massive module with just the same operation repeated over and over again. Right? And so
it's combinatorial?
Huge combinatorial divider.
mm-hmm. And so
So how fast is it when it's combinatorial?
instant. It's unclocked.
Well, no, that's not the point because there's a propagation time through all the steps.
I'm the coder.
It can't be instantaneous, right? It's got a propagation time. So it's blocking code, right?
Mm-hmm.
So there's an order to the operation. It's not clocked, but there's an order to the operations. It has to physically go through the logic that generates that thing.
It's faster than the clock version, though, that's for sure.
So, not necessarily. So each, if we take a closer look at the clock version, what's happening is that so this is like the main loop, I guess. It's taking some divisor and then right shifting it by one at each iteration, right?
Yeah, it's a shift
But
and then add.
it's if the condition like that modifies the quotient only changes a single bit, right? So these operations are actually independent of one another, right? If you right shift, you can right shift the starting divisor by one and then get that bit and then also right shift it by two at the same time.
If they're independent, then then it's combinatorial, then they will truly be in parallel.
Yes. Because you right shift it, like how it codes it, it just right shifts it by, it has some counter in Python, right? It's like a for loop, right? And then it just creates another variable for that. And then it decrements the number you shift it by. And so all of this is clearly not spatially efficient. It proves like the power of what a library like this can take advantage of in a language like Verilog. And so this actually brings up another portion of this library, which is the testing side. And so I've also interfaced it. So in addition to the modules you can write, there's also test bench objects, right? And what these test bench objects allow you to do is interface with ModelSim directly. So I just turned this simulate function with the argument headless from true to false. And so now if I run it, it will pop up with ModelSim and show me all of the waves that I ask it to. And so maybe you're asking, okay, what waves am I asking it to show me? And so so all of these modules are of a class of module that I refer to as a target function. And a target function can be abstracted to the notion that a target function has a set of inputs. At some point, those inputs are going to be valid, right? When those inputs are valid, the target function does something, and at some point after that, the target function is going to be done, right? So there's a valid flag that the instantiator is responsible for, and then a done flag that the module can raise when the functionality is terminated, right? And so the test bench detects all of the modules that you instantiate, and if they're all target modules, it stops the simulation when all the done flags are raised, and so it concatenates, right? It's like a bitwise AND of all these 1-bit signals, right? And so, but what's even better is that a part of the test bench is you have access to this presim function, where all of these Python signal objects, right? Let's say self.div nums dot quotient. I think that's one, right? Let's say we want to see the quotient of the divider's internal module, not what's even at the top level test bench. We do self.log self.div.quotient. So if we run it again, and so there's our quotient, right? It wasn't there before. And so it allows you to really rapidly simulate. But what's even better is that I've also added the ability for, in addition to showing you the wave out of the form, it logs it to a file, and then I wrote a parser that parses it, and so you can, there's another function called expect that not only logs it, shows you the wave when you want to see the model sim, but you can also give it an expected value, and then it returns the mean squared error and how it deviates from your expected value. And it works for arrays because it's a mean squared error, right? For a single value, it's just one item, but and so that was instrumental in determining a very complicated system like a neural network. Like I would not have been able to build that without the ability to I make this test, this small change. How does it impact the greater network? And so I can see how the mean squared error changes over time. And notice it's not the mean squared error of the accuracy of the model. It's the error between how it deviates from its Python counterpart, which is obviously error tested and error corrected, right? And so that's super important for figuring out,
If I can interrupt, we have 7 minutes till the next demo.
Sure.
So.
Okay. So, showed you so that's the Python module. So neural network, part of the video we started with. So, if we take a look at the file structure one more time.
So can I just briefly ask that, am I correct that a lot of the motivation for all this infrastructure that you built was there are all these tools for building and training neural networks in Python?
Yes.
And the objective was to use these existing Python tools to build a neural network to accomplish some goal, and then build this infrastructure that just takes that and translates it to the FPGA.
Exactly. That was the goal from the get-go.
Okay.
I think even a future goal is to not only run inferences on the FPGA, but to also train, because what we did was we used TensorFlow, which is a Python library, to train our model against test examples that I generated. I handwrote 6,000 digits, and then we used those training examples, trained on TensorFlow, and exported the weights, and then fed the weights back to Verilog, and then use it there.
Okay.
We want to actually develop the weights, in Verilog too, but that's very computationally expensive because you're doing all these matrix multiplications by computing the gradients and partial derivatives of all these various functions, and that's very computationally expensive to do just in software. So we think it would with the hardware accelerator too, it'd just be way faster.
And I think like my personal objective, because I had this idea about a year ago, and like my personal objective is so CPUs are not optimized for machine learning because they're single cycle processors, right? GPUs have more throughput, but they're not perfect for machine learning, and they're also expensive. And so I think it would be really cool to have an open source library that would enable anyone to have high performance computing at their fingertips for very cheap. And so that was my goal, and making it as the reason I added all this structure to abstract a lot of the really low level stuff away was to make it as easy to build new modules and as pain-free as possible. And that's why I chose Python to do it, because Python is very painless. And so, I hope people use it. I'm going to work on it more. This is something that wasn't, this is class agnostic. This class gave me the opportunity to do this. I had this project in mind for a while. But I know you guys have to skedaddle in a minute, and so if you have any more questions, just while I pull up the demo again.
And so you needed just a sort of a toy problem to solve to help build this infrastructure, so you chose digit recognition.
It's like the hello world of neural networks. We were trying to, right, because neural networks get very big very quickly, and we what's the word?
So initially we implemented a single layer convolutional neural network, but we found that because of the max pooling operation I just showed you, it reduces that feature map. It cuts it in half each time. So with only one layer, we only cut our 28 by 28 in half.
Like we had over 100,000 weights, and we were doing our bit size to start when we because the smaller fixed points you have, right, bit width, the less precision you have, right, or the less room for error, because these networks can go from like big integer numbers to very small decimals really easily. And so we started out with 44.44 and a model that was massive. It had over 100,000 weights. And obviously no way that was getting on there. And so I put a lot of work into the structure side, but Kenneth absolutely would not have been able to do it without him. Like, he reduced the model to about 3,000 weights, and we did 6.10 fixed point.
Okay.
And so, I mean, just today, I spent all of today,
doing 40 convolutions with crazy indices that Joe was able to map out. It's absolutely insane.
It's a headache, but the oh god, I'm so tired.
So
Wrap it up.
let's see it work.
Wrap it
Yeah. So
Yes.
so you can
A 7 again?
put a number in here and predict,
7's good.
and
You gotta slow it down, my guy.
so that's showing that the Python model predicted 5,
I didn't even think that was a 5.
and then on the FPGA,
That's better than human
the
performance.
hex display is also indicating that
I
that's
thought it was
a
an
5.
S. Very impressive.
Very nice.
So
Very
that's
nice.
what the second convolutional layer was so necessary in capturing that, because if you had written a 5 on that left spot, because it wouldn't have worked, because only one convolutional layer doesn't capture that spatial dependence. So that second one was
Very nice.
instrumental in compressing it.
Cool. Thank you guys.
Yep, thank you.
Very nice.